Hello, Math 1040 team. Today I would like to start looking at section 5.1, exponential functions. In this chapter, we will explore exponential functions. Exponential functions arise when a quantity does not grow by a constant amount, but by a constant growth rate given as a percent. In business, this occurs when we want to describe the balance in a bank account or some other savings instrument in which earnings are reinvested, such as with mutual funds and retirement accounts. An exponential growth or decay function is a function that grows or shrinks at a constant rate given as a percent. When you're reading questions in your homework, look for this word where they say something grows or shrinks as a percent. This is an indication that you will be looking at an exponential function. The equation can be written in the form f of x equals a times 1 plus r raised to the x, where a is the initial or starting value, r is the growth rate or decay rate written as a decimal, and 1 plus r is referred to as the growth factor or growth multiplier. Graphically, you would like to see how an exponential function is different than a linear function. Where a linear function has a constant slope, a constant growth, an exponential curve, the slope is changing as you go through time. It gets steeper and steeper. To see the difference between linear growth and exponential growth, consider two companies. Company A has 100 stores and expands by opening 50 new stores each year. Company B also has 100 stores and expands by increasing the number of stores by 50% of their total each year. So, looking at a few years' growth for these two companies, we can see Company A starts with 100 stores. After 1 year, they added 50 stores. Oh, my pen's messing up. To now have 150 stores. After the second year, they add another 50 to now have 200 stores. Why is this doing that? After 3 years, they add another 50 stores, and now they have 250 stores. While Company B starts with 100 stores, after the first year, they'll add 50% of that 100. And notice that 50% of the 100 is calculated by 0.50 times 100. And the original 100 plus that 50% now gives the new total of 150 again. After the second year, they grow by another 50%. And the 50% of the 150 that was there now gives them 225 stores. After the third year, they grow by another 50% of that 225, which gives them 337.5 stores. So notice that with percent growth, each year the company grows by 50% of the current totals. So that as the company grows larger, the number of stores added grows as well. To see a pattern and to simplify the calculations, let's look at the numbers again. And notice that after 1 year, the number of stores for Company B was the original 100 that it started with, plus the 50% of that 100. Notice that you have two common factors of 100 that you can pull out, leaving the 1.50, the growth multiplier, and ending with the 150 stores that they had. After 2 years, they started with 150 stores. They grew by 50% of that 150. Again, notice the common factor of 150 that you can pull out, again, leaving that growth multiplier 1.50. But recall where the 150 came from. It was the 100 times the growth multiplier. So if we replace this 150 with the 100 times the growth multiplier, we now have two factors of the growth multiplier, and so I write it with an exponent. After 3 years, We started with the 225 stores. We grew by 50% of 225. Again, notice the common factor of 225 that I can pull out, leaving the growth multiplier. But again, remember where the 225 came from on our previous line. If we replace the 225 with the 100, 1 plus 0.50 squared, we now have 3 factors of the growth multiplier, which I'll write as a cube, and we have the 337.5 stores. From this, we can generalize to show a 50% increase each year. We would multiply by a factor of 1.50. So after n years, our equation would be b sub n is equal to 100, 1.50 raised to the n, and in general, we have an exponential curve of this form. Graphically, when we look at the two different companies, again, we'll see a linear growth. For company A, grows by a constant amount, while for company B, an exponential growth curve where the amount of increase increases each year. I hope this is making sense. Let's look at an example more like what your homework is going to look like, though. The number of players of a popular smartphone game, Candy Crush, was initially 11,000. And it grows by 5.7% each year. Notice that 5.7%, that tells me that we're talking about an exponential growth. Suppose P represents the number of players of the game and T the number of years since the game was introduced. Write an exponential model for the number of players in this form. Here we're looking at just form recognition. They tell us A, the initial population, and they tell us R, the growth rate. So our exponential growth curve would look like P of T, the 11,000 that we start with, times the 1 plus, write your percent as a decimal, 0.057 raised to the T. Now, most of the time, it's common that we rewrite this sum as just a single decimal. And so I'm going to write this as 11,000 times 1.057 raised to the T. This is our exponential growth function that models the number of players of Candy Crush. Part B. What will be the number of players in 4 years? Here we're asked to calculate what is P of 4. And that would be the 11,000 times 1.057 raised to the 4th. And I'll use our calculator to help me with this. Make sure that you can enter this in your calculator. Everybody enters exponents differently. On mine, it'll be the 11,000. I'm going to use parentheses for the growth multiplier. Raised to the 4th power. It asks us to round to the nearest person, so I'm going to round this to 13,730. And if I round this to the nearest person, I'm going to call this 1,731 people. Okay. Now, our next example talks about the number of people in a certain region that watch Amazon Prime. I would like to give you a moment to do this question on your own. So if you could, please pause the video and work this out. It is very similar to the last example we did. After you've worked it out, unpause it and look at the solution that I will write. Let's look at our solution. A number of people in a certain region that watch movies on Amazon Prime has an annual growth rate of 12%. If it is estimated that the number of people that watch movies on Amazon Prime in 2016 was 28,900, How many will watch movies on Amazon Prime in 2022? Let t equal 0 correspond to the year 2016. This is our starting amount. Here, our exponential growth function would look like p of t equals our starting amount, the 28,900, times our growth multiplier, which I'm going to write as 1.12 raised to the t. We're asked to find out how many are watching Amazon Prime in 2022. Notice that 2022 is 6 years after 2016. So we're going to be looking at P of 6. And we'll evaluate this as 28,900 times 1.12 raised to the 6th. Make sure that you can duplicate this value on your calculator. However, when I do it, I get 57,000. I'm going to round this to the nearest number of movies, so I'm going to call this 57,043 movies. Let's look at another example. Again, I'd like you to pause the video and try working this on your own, and then after you work the video, come back and look at my solution. Let's look at the solution. A vehicle purchased for $32,500 depreciates, it decreases, it decays at a constant rate of 8% per year. Determine the approximate value of the vehicle 11 years after it was purchased. Here, our exponential growth curve is going to look like P of t, your starting amount, the 32,500, times 1 plus your growth rate, which actually is a depreciation, so I'm going to write it as negative 0.08 raised to the t. Again, it's common to rewrite this inner piece right here. And so if I simplify this, this will be 32,500 times 0.92 raised to the t. We are asked to calculate the value of the car 11 years after it was purchased. So we'll be looking at P of 11. And using our calculator, I get P of 11 to be, again, put in your parentheses to identify your growth multiplier, raised to the 11th power. And I get, after 11 years, the value of the car has decreased to 12,988. And since we're talking about money, I'm going to round this to the nearest penny and call this 21 cents. Let's look at another example. This one would be slightly different. A house valued at $120,000 in 1995. The value appreciated, it grew to $170,000 by the year 2007. What was the annual growth rate? So notice in this problem, they didn't tell us the growth rate as a percent, but are asking us to find this on our own. Now we know this follows an exponential model still, and so if we start using some of the values we know, I can write our exponential growth curve as P of t, our starting value, the 120,000, times 1 plus r, your growth multiplier, raised to the t. And our goal now is to figure out what is r, our growth rate. And I'm going to use the fact that we know in 2007, which is 12 years later, the value of the house has increased to 170,000. So we can write then 170,000 would equal to original 120 times your growth multiplier raised to the t, but here t is going to be 12 years. And now I'd like to solve for r. So let's first divide both sides by this 120,000. Of course, you can get decimals here if you'd like, or you can leave it as a fraction. If I were to rewrite this as a decimal, I think I get this to be, and I'm going to write it to 4 decimal places, 1.4166. And this would be equal to the 1 plus r raised to the 12th. Now, I would like to solve for r, and so I need to get rid of this power, the 12th power here. And I'm going to do that by taking the 12th root, like a square root, but the 12th root of each side. And the 12th root of the 1.4166, well, let's calculate on my calculators just so you can see how I do this. Everyone's calculator is a little bit differently, but on my calculator, I have to hit the value of the 12 first. And then located under the math key, option number 5, it has an xth root. And so my calculator interprets that as the 12th root of 1.4166, which I get, and I'm going to write this again to 4 decimal places, 1.0295. This is what I get for 1 plus r, the growth multiplier. But since we were looking for just in this problem the growth rate r, we can subtract 1 from both sides and say now that r is 0.0295 or 2.95% is the growth rate as a percent. But it might be helpful if we just wrote our exponential growth curve again so that we can see it. I think we're going to need it in step B. And so I'm going to write the exponential growth curve P of t, our starting house value, the 120,000, times the 1.0295 raised to the t. And this is going to be the exponential growth model we use for part B, where it says, assuming the house value continues to grow by the same percentage, what will be the value of the house in 2012? Now notice 2012 is 17 years after 1995. So we'd be looking here for the value of P17, which would be the 120,000, 1.0295 raised to the 17. Now make sure you're able to duplicate these calculations on your calculator. Since all of our calculators are different, this is something that we do want to learn. Make sure I get the 120,000 in there correctly. Times your growth multiplier raised to the 17th power. And I calculate this value as 196,000 711. And I guess since we're talking about money, let's round this to the nearest penny and call this 26 cents would be the value of your house in the year 2012. Let's move forward and look at a different aspect or a different property of these exponential functions. Let's consider the graphs. Given the function f of x is equal to a times 1 plus r to the x, or if we want to simplify this, ab to the x, where the b is the 1 plus r, we'll notice that our curve always has an intercept at 0a, the coefficient, the starting value. To see this, notice that if we evaluate our function at 0, then we would have f of 0 would be a times b raised to the 0. Recall that any number raised to 0 is always 1. And we have a value of a when x is 0. So they always have an intercept at 0a, and that's going to be where it crosses the y-axis. The value of b, which we refer to as the base, determines the rate at which the graph grows. If the base b is greater than 1, then we have an exponential growth curve. If the value of the base b is between 0 and 1, then we have a decaying or decreasing exponential growth curve. Notice the graph will always have a horizontal asymptote at the line y equals 0. The domain of the function, all real numbers. It goes forever to the left and forever to the right. And the range of the function is all positive numbers. To get a better feeling of the effects of the base b on your graph, examine the set of graphs below and notice that the closer the value of the base b is to 1, the flatter the graph. So here where your base b 0.9, this is a much flatter graph than all of the rest of them. For values of b greater than 1, and I'm looking at these ones here, the larger the value of b, the steeper the graph. So as your base goes from 3/2 to 2 to 3, your graph gets steeper and steeper and steeper. For values of the base b between 0 and 1, the closer that b is to 0, the steeper the graph. So I'm looking at 1/2, 1/3 to the x. As your base gets smaller and smaller, it gets steeper and steeper. And also notice that all three of these go through the point 0, 1, the y-intercept. To explore this a little more, I have several functions here. I think there's 5 of them and 5 different graphs. And I'd like to take a moment to give you the opportunity to match each of these graphs. So if you could, please pause the video and take a moment to determine which equation describes which of these functions, f of x, g of x, h of x, on the graph here. After you've taken a moment to think about it, unpause the video and come back so you can see my solution. Let's look at how I can match these up. One of the things I'm looking at right away when I look at these equations is the starting value, your coefficient. Remember, your starting value, your coefficient, is always the point that your function needs to go through when x is equal to 0. So I notice that when x is equal to 0, this one goes through 3, or 0, 3. This one goes through 0, 4, 0, 3, 0, 3, 0, 3. And so right away when I'm looking at my graphs, I know that this one, I think it's labeled p of x, is the only one that goes through 0, 4. So that tells me that this has to be described by the graph of p of x. Now for the others, I'm going to use the value of the base b to help us determine it. Remember, if your base b is bigger than 1, then this is going to be an exponential growth curve. And remember, the closer that your base is to 1, the flatter your graph, and the larger the value of the base, the steeper the graph. That tells me that this, not that one, I want to look at, we've already did that one, so just these two actually. So I'm comparing these two, and I'm noticing that the base of 1.5 tells me this is going to be a steeper graph, this is going to be a flatter graph. And so when I'm looking at these, I'm looking at both h of x goes through 0, 3, and r of x, this green one. And notice that h of x is steeper, that has to be the one with the larger base. This would have to be the graph of h of x. While this one would have to be the graph of r of x. For the two graphs that are remaining, I'm noticing that the value of the base b is between 0 and 1. And so these have to be decreasing exponential functions, so either f of x or g of x. Remember, the closer that the base b is to 1, the flatter the graph. And so that tells me that this first one, 0.7, closer to the 1 than 0.5, this has to be the graph of f of x. This one has to be the graph of g of x. Now, we're not going to be doing a lot with the graphs of exponential functions on our homework, but I do want to emphasize that we know whether a graph is increasing or decreasing based on the value of this growth multiplier, this base. Let's look at an application of these exponential growth curves. Compound interest. Typically, bank accounts and other saving instruments in which earnings are reinvested, such as with mutual funds and retirement accounts, they utilize compound interest. The term compounding comes from the behavior that interest is earned not on the original value, but on the accumulated value of the account. Compound interest can be calculated using this formula. You are not going to be required to memorize this formula. I will provide it on future exams, but you are responsible for knowing how to use it. In this formula, the left-hand side, A of t, is your account value. A, your starting amount of the account, also called the principal. R, your annual interest rate, given as a percentage. K, the number of times that you compound per year, and T, your time in years. Let's look at some examples. Let's compare the following two investments. Which has a larger ending balance? Jason invests $9,735 at 9% interest per year in an account that was compounded quarterly for 29 years. So his value using compound interest would be A of t equals A, your starting amount, which he started with the 9,735, times 1 plus R, your interest rate, written as a decimal, 0.09, divided by K, the number of compounding periods in 1 year. Here they're telling us we're compounding quarterly, 4 times per year. Raised to the exponent of kt, so again, 4, because we're doing it quarterly, times t. And we're asked for the value of Jason's investment after 29 years. We're looking for A of 29. So raised to the 4 times 29. Now, a lot of people are tempted to put this in calculator in pieces, but this introduces rounding errors. So I'd like to encourage you to put this in your calculator all at one time, using parentheses. So we have our starting amount, the 9,735, 1 plus our interest, 0.09, divided by the number of compounding periods per year, raised to the exponent of 4 times 29. Now, everyone's calculator is different. My calculator specifically lets me know I'm working on an exponent, but if yours does not, you may need to put parentheses around this so that your calculator knows that the 4 times 29 all belongs as an exponent. And since we're talking about money, let's round this value to the nearest penny. I see this coming out as 128,611 and 76 cents as the value of Jason's investment. Now let's compare this to Alicia's investment. Alicia set up the same investment as Jason, except she invested twice as much money for half as long. So the value of Alicia's investment, A of T. Well, she invested twice as much, so not 9,735. She would have invested 19,470. 1 plus, now she had the same interest, 0.09, compounded quarterly, raised to the exponent of 4 times. And she only did it for half as long, so not 29 years. That would be 14.5 years. So let's see what that looks like. 19,470. 1 plus your interest rate divided by the number of compounding periods raised to, again, your compounding periods times the amount of time that she invested, which was 14 and a half years. And I get this coming out to be 70,768. Again, since we're talking about money, let's round this to the nearest penny and call this 23 cents as the value of Alicia's investment. Notice that even though she invested twice as much money, she only used half as much time, and that dramatically affected how much interest she was able to earn over the lifetime of her investment. Let's look at another example. And it was weird. It started this on the wrong page. I'm going to have to fix that. This won't affect our lecture, though. Let's continue to compare how changing the number of compounding periods affects the ending balance of an investment. Consider you invest $3,000 in an investment account paying 7.25% interest for 10 years. How much will be in the account for the following different compounding periods? So here we want to investigate how does changing your compounding periods change your account balance. Now, all of our formulas will be almost the same here, except for how we're changing K. If we're doing interest annually, K is going to be 1 because we compound interest once a year. If we're compounding interest quarterly, we're doing it 4 times per year. If we're compounding interest monthly, we're doing it 12 times per year. And if we're doing interest compounded daily, we're doing 365 times per year. Now, I'd like you to be able to calculate the value of the account for each of these different compounding periods on your own. And so if you could, please pause the video again and determine what the balance will be for each of these different options. After you've calculated these, unpause the video and verify we get the same answers. Let's work it out now so we can compare. If you're compounding interest annually, then your account balance would be the starting amount, the 3,000, 1 plus your interest rate written as a decimal, divided by the number of times you compound per year, which we're doing once, raised to the 1 times 10. While if we're doing it quarterly, then our account balance would look like this. Like if we're doing it quarterly, we're doing it 4 times per year, raised to the 4 times 10. If we're doing it monthly, then we're compounding 12 times per year, raised to the 12 times 10. If we're doing it daily, then we're compounding interest 365 times a year, raised to the 365 times 10. I'd like you to verify that you can get each of these on your calculator, but in terms of this video, I'm just going to write the answers for us. If you compound annually, you should have an account balance of $6,040.80. If you compounded interest quarterly, the value of your investment should be $6,154.11. Monthly, $6,180.70. While if you compound daily, your account balance should be $6,193.75. What we should observe is that as you increase the number of compounding periods, the amount we earn also increases. However, there is a limit to compounding. Notice that the increase from annual to quarterly is larger than the increase from monthly to daily. So what I'm asking you to notice is the amount that you gain from when you go annually to quarterly. Roughly, without calculating this is about $114 more of interest that you would have gained. While when you go from monthly to daily, you only have an increase of, it looks like it's around $13. This might lead us to believe that although increasing the frequency of compoundings will increase our result, there is an upper limit to this process. To see this, imagine we invested $1 at 100% interest. Wouldn't that be nice? For 1 year for the following compounding periods. Notice that the value of $1, if you compounded interest annually 1 times per year, that after 1 year you'd have $2. Semi-annually, twice a year, $2.25. Quarterly, monthly, daily, hourly, once per minute, once per second. Notice that this value, the value of $1 after 1 year, is approaching an upper limit. This upper limit is so important in mathematics, it gets represented by its own letter E. Specifically, E is the letter that is used to represent this value as k approaches infinity. Most people remember E as the number 2.718281828, or just E is about 2.7. Because E arises when the time between compoundings is very small, every second, it allows us to define continuous growth and gives us a new function, f of x equals e to the x. Let us now look at the continuous growth formula. Continuous growth can be calculated using the formula f of x equals a times e raised to the rx, where A is the starting amount, and R is your continuous growth rate. While it does not make sense to talk about money being compounded continuously, we can apply this model to chemical reactions, the growth of populations, and even radioactive decay. Let's look at an example. Suppose a population of bacteria has an initial population of 20,000 and a growth rate of 4.4%, compounded continuously. What is the population after 25 days? Here, our continuous growth model would look like f of x equals, again, A, your starting amount. We started with 20,000 bacteria, times E, raised to your R, your growth rate, written as a decimal. And 4.4% would be 0.044 times x. We're asked to calculate the population after 25 days, so we'd be looking at the value of F25. Now on our calculator, again, everyone's calculator is slightly different. My calculator has an e to the x, it's in blue, it's underneath this ln key. So when you type in e to the x, you're probably going to have to find it on your calculator where that is located. Now for this problem, we have the 20,000. And to get to my exponential function e to the x, I'm going to do second to get the e to the x there. Notice again, it puts it all as an exponent. On your calculator, you might have to put parentheses there. 0.044 times 25. And I get this to be 60,083.32 bacteria. Now, obviously, you can't have 0.32 of a bacteria, so it might be reasonable to round this to just call it 60,000. If I round this to the nearest bacteria, it'd be 83 bacteria. Now, this is the last example I have for you in Chapter 5.1 Exponential Functions, so I'm going to end this video here. I will work on another video for Chapter 5.2 Logarithmic Functions next. I hope this has been helpful, and I'll see you guys next time.